Chapter 5, the Relational Data Model and Relational Database Constraints. In this chapter, we will talk about different relational model concepts, constraints, as well as take a look at what a relational database schema looks like, and also talk about different update operations and how to deal with constraint violations. You've already seen informally what a relation is in MySQL. Informally, a relation looks like a table of values. A relation typically contains a set of rows, or records, again like you saw in MySQL. The data elements in each row represent certain facts that correspond to a real-world entity or relationship. In the formal model, rows are called tuples. Each column has a column header that gives an indication of the meaning of the data items in that column. Think something like product name. In the formal model, the column header is called an attribute name, or just attribute. We've already talked about what it means to be a primary key, but we'll define it more formally here. Each row in the database table has a value of a data item, or set of items, meaning the columns, that uniquely identifies that row in the table. This is referred to as the key. So in the student table, for example, social security number is the key. Sometimes row IDs or sequential numbers are assigned as keys to identify the rows in the tables. These are called virtual keys. Here's an example of a relation. You have the relation name, or the entity name, the different attributes which are assigned as columns or field headers, and then you have different tuples. You've already seen tuples as records, but you can also think of a tuple as a collection of values that gets assigned to each field. Let's take a look at the formal definition of a schema. A schema of a relation is denoted by the name of the relation, or R, and then in parentheses all of the different field names, so A1 through AN, depending upon how many names there are. So R is the name of the relation, and the attributes are A1 through AN. For example, here we have a customer relation, and we have customer ID, customer name, address, and phone number as attributes in the relation. We say that customer is defined over these four attributes. And as you saw with data type, in MySQL, each attribute has a domain or a set of valid values. For example, the domain of customer ID is 6-digit numbers. A tuple is an ordered set of values, yes, ordered set, enclosed in angled brackets. Each value is derived from an appropriate domain. A row in the customer relation is a 4-tuple and would consist of 4 values. For example, we have the customer ID followed by the name, the address, and the phone number. This is called a 4-tuple as it has 4 values. It is a tuple or a row or record in the customer relation. A relation is a set of such tuples. So in other words, you think of a database table with all the different records. The relation is the abstract formal way of looking at this. We've talked a little bit about what a domain is in the sense of data type, but domain can also mean different valid numbers as well. For example, you wouldn't have a negative number for somebody's age. Here's another example of the logical definition of domain. USA phone numbers are the set of 10-digit phone numbers valid in the United States. The domain also has a data type or a format defined for it. So here we can see the format, parentheses for the area code, and a hyphen, and we can also set it to be an integer or a decimal or a varchar. The attribute name designates the role played by a domain in a relation, and it can be used to interpret the meaning of the data elements that correspond to that attribute. So for example, if we have something like social security number, we can use that to interpret the numbers that are in the column, rather than just thinking of them as some random digits. The relation state is a subset of the Cartesian product of the domains of its attributes. Okay, so what is the Cartesian product of the domains of its attributes? All this means is you think of all the different possible combinations of values that you could have in a record defined by the domain, and all of those together represents the relation state. So it's the set of all possible values that all the attributes can take. So for example, the attribute customer name is defined over the domain of character strings of maximum length 25. The role that these strings play in the customer relation is that of the name of a customer. So here's a comparison of the things that we've looked at in MySQL and the now formally defined terms. So for a table, we have abstractly a relation. Column header or field, we have an attribute. All possible column values, that would be a domain. A row or a record would be a tuple. Table definition, that's our schema for the relation. And the actual populated table would be a current state of the relation. Here's an example of a student relation. You can see the relation name with the possible tuples again. as well as the attributes, and each one of these attributes has a domain. When we start to talk more formally about relations and schema, we should also talk more formally about constraints. We've already formally defined certain constraints, but we should talk about them again here. Constraints determine which values are permissible and which are not in the database. And there are three main types. Inherent or implicit constraints. These are based on the data model itself. So for example, you can't have a list as a value for an attribute. Some constraints are schema-based or explicit. These are expressed in the schema by using the facilities provided by the model. So for example, like cardinality, that the maximum number of classes a student can take is many. And then there are also application-based or semantic constraints, which are beyond the expressive power of the model and have to be specified and enforced by the application programs themselves. We've talked about relations. We have relational integrity constraints. These are conditions that must hold on all valid relation states. And we've already talked about the main types of constraints: key constraints, entity integrity constraints, and referential integrity constraints. Another schema-based constraint is the domain constraint that states that every value in a tuple must be from the domain of its attribute, or null if allowed for the attribute. So again, if we've specified that we have varchar for a particular field, should be within that domain. Let's talk a little bit more about key constraints. We've already established that if you have a primary key, every value for that key should be unique. You may have seen an error in which you tried to add duplicate primary key values into your database. So here we want to define the difference between a superkey and a key. We have some formal definition that I think will become clearer once you see an example. So a superkey for a relation is a set of attributes with the following condition: that no two tuples in any valid relation state can have the same value. So if you have a superkey, whether it's composed of one attribute or many attributes, they have to be distinct. And this condition must hold in any valid state. A key of the relation is a minimal superkey. So you figure out if you have a superkey so that if you take a look at two different tuples or two different rows, that they have a unique collection of values. And then you ask yourself, well, is this superkey also a key? Is it a minimal superkey? So that if I take out an attribute from the set of attributes, that it is actually no longer unique. So a key is a superkey, but not vice versa. Let's take a look at an example. This is actually a very nice example from Wikipedia. Here we have a relation or a table with English monarchs. You can see that we have different tuples that are composed of the monarch name, monarch number, and royal house. So for example, we have a tuple composed of Edward to Plantagenet. We should figure out what a superkey is if there are multiple superkeys, and then what a minimal superkey might be. So the first thing we want to do is list out all the sets of the attributes. So you can see that we're using the field header name. So for example, we can take just the monarch name, we can take just the monarch number, just the royal house. We also have the combinations of the monarch name and the monarch number, the monarch name and the royal house, the monarch number and the royal house, and then the set of all three, so monarch name, monarch number, and royal house. Now, for a set of these to be a superkey, all that has to hold is that if you take two tuples, that they are distinct. So we could take a look at this last set of fields, the name, the number, and the house. And if we take a look, they are actually all distinct. So monarch name, monarch number, and royal house is a superkey. You look at any of the tuples and you can see that they're all distinct. But the question is, can we find a minimal superkey? So what we're going to do next is get rid of any set that does not meet the superkey requirement. So for example, here's some easy ones. Ask yourself, monarch name, is everybody unique? And the answer is clearly no. We have two cases of Edward. Is monarch number unique? Well, we have two cases of 3, so no. And the same goes for royal house. So these are not superkeys. We don't have unique values. Then we have to look at the other combinations that were presented to us, including the combination of monarch name and monarch number. So we look down, and at each of the combinations, we have Edward II, Edward III, Richard III, and Henry IV. Now those are all different. So that is a superkey. What about monarch name and royal house? Well, that's not going to work either because we have two tuples, as it says here, that have Edward Plantagenet. So that's not unique either. After we've looked at every single combination of the fields, we then are left with the following. So we're left with monarch name, monarch number as a combination that could be a minimal superkey, and monarch name, monarch number, and royal house. So this set now of monarch name and monarch number is a superkey. It is also a candidate key because we're considering it for primary key. The last thing that we have to do before formally deciding that it is a primary key is check to see if it is a minimal superkey. And so it is a minimal superkey if when you try to remove one of the fields from the set that you end up with duplicate values. So for the one where we have all three, we can see that if we take out, for example, the royal house, that we don't get duplicate values. So that's not a minimal superkey. But for the combination of monarch name and monarch number, if we try to remove one of those, you'll see we get duplicate values here if we try to remove monarch number, and we get duplicate values here if we try to remove monarch name. So this candidate key is also a minimal superkey and is a great key to be used as a primary key. Wikipedia adds this nice note that you can't just examine one set of tuples in a relation and expect to determine the superkeys. So a superkey property is best determined from what's called the functional dependencies. And that's something that we're going to look at in the next lesson. If you have a relation with n attributes, so for example 3 here, then the maximum number of superkeys possible is 2 to the n. So in this case we had 2 to the 3, or 8. The next thing that's presented is an example using the car relation schema. And so I encourage you to take a look at it by yourself to see if you can follow the same procedure that was presented in the monarch example to determine superkey and a minimal superkey. If a relation has several candidate keys or minimal superkeys, then one is chosen arbitrarily to be the primary key. As we saw before, we underline the primary key attribute or attributes in order to indicate that it is a primary key. And in the car example, serial number is eventually chosen as the primary key. Primary key, again, is used to uniquely identify each tuple in a relation. And it is also used to reference the tuple from another tuple. So the general rule is to choose as a primary key the smallest of the candidate keys in terms of size, so the number of attributes that are available. This is not always applicable. The choice is sometimes subjective, but that is a good rule to use. In this car table, we have 2 different candidate keys, license number and engine serial number. So candidate key, we've gone through the process of checking to see first if it is a superkey, and if you only have one attribute in the superkey, then it also serves as a minimal superkey. So here you can see it's a little bit subjective. We've chosen to use a license number as a primary key, likely because that's more human readable than the serial number. We've introduced a relation schema. A relational database schema is a set of relation schemas that belong to the same database. This is basically the collection of table schemas. The formal definition calls the entire database schema S, where S is the set of all of the relation schemas from R1 to Rn, and a set of integrity constraints. Here is a relational database schema example. We can see the collection of all the different relation schemas, everything from employee down to dependent. And you can see that the primary keys are underlined. The schema serves as the blueprint, as we've talked about earlier. A relational database state is when you have different relation states, such that each relation is a valid state and all integrity constraints are satisfied. A relational database state is sometimes called a snapshot or instance, but we're not going to use the term instance because it also applies to just a single tuple or record. A database state that does not meet the constraints is an invalid state. Each relation or table will have many tuples or records in its current relation state. And the relational database state is the union or the sum, the collection of all of the individual relation states. Whenever the database is changed, a new state arises. And here we have the basic operations for making changes to the database, including insertion, so putting a new tuple into a relation, or inserting a new record into a table, deleting an existing tuple from a relation, or deleting a record from a table, or modifying or updating an attribute of an existing tuple. So we could, for example, change somebody's last name. Here is an example of a populated database state for the company database. You can see that each table has records, so each relation has tuples. We have already talked about integrity constraints. Here we'll formally define them. So entity integrity, where the primary key attributes of each relation schema cannot have null values in any tuple. So if you have a primary key, it has to have a value. This is because the primary key values are used to identify individual tuples. And if the primary key has several attributes, null is not allowed in any of the attributes. Other attributes in a relation schema can be constrained to not be null, but they're not primary key. So referential integrity is a constraint that involves two relations, and it is used to specify a relationship among tuples in two relations, the referencing relation and the referenced relation. So think about the gold star schema. The referencing relation would be the employee table, and the referenced relations would be the position and the location tables. Here's the formally stated referential integrity constraint. The value in the foreign key column or columns of the referencing relation can be either a value of an existing primary key value of a corresponding primary key in the referenced relation, or it actually can be null. So if you have a foreign key field, it can be null, but if it is not null, then it has to be an existing primary key value. Also, if it is null, then it can't be part of a primary key. So for example, in the many-to-many case, you couldn't have, say, course ID or student ID either be null, because they both serve as a primary and foreign key. Here we have the different update operations on relations: inserting tuples, deleting tuples, or modifying tuples. When these operations are performed, the integrity constraints should not be violated. Sometimes several update operations may have to be grouped together, and sometimes updates propagate to cause other updates automatically. This might be necessary to maintain integrity constraints. What are some possible violations for each operation? So if you are inserting a new record into the database, first you have to be sure that the attribute values are within the domains. We have a domain constraint. We also have the other constraints we talked about. If the value of a key attribute already exists, so if you already have a specific value for a primary key, then you won't be able to make that insertion. If you try to insert something with a foreign key value that doesn't exist as a primary key, then you're going to violate referential integrity. You won't be able to insert that record into the database. And finally, you can't insert a record where the primary key is null. If you try to delete a record from a database, then you might violate referential integrity, but that would be the only possible constraint violation. So if the primary key value of the tuple being deleted is referenced from other tuples in the database, so in MySQL, if you try to delete the position table values before deleting them in the employee table that is acting as a referencing table, you're going to have issues with referential integrity. And so you can remedy this with several actions that we may talk about at a later time. The easiest option would be to set null. So if you just set the foreign key of the referencing tuple to null, then you won't have that issue. If you run an update query, you might violate domain constraints if you're trying to add values that aren't within the domain, and you might also violate not null constraints if you're trying to insert where there's a null value and it's supposed to be not null. Any of the other constraints might also be violated. If you're changing the primary key, it has to have a value that's unique. If you're changing the foreign key, it has to already be a primary key in the reference table. For other ordinary attributes, you just have to make sure that the value is within the domain. So now you've gotten to see the formally defined relational model, as well as database schemas, relation schemas, and formal definitions of each of the different constraints, as well as how the constraints might be violated.